Scientists in Switzerland fired up the world's largest particle collider. The start of the collider came with objections. Some feared the collision of protons could destroy the Earth by creating micro black holes.
Are conducting experiments which may potentially create a black hole.
There's a lot of talk that the energy levels in the LHC can actually cause the universe to rupture.
The experiment is making some nervous that it could create a cosmic black hole.
The whole global warming thing would be moot because there'd be no Earth anymore.
They may kill us all.
When news that physicists were building the world's most powerful particle collider hit the mainstream in 2008, not everyone was so on board. Rumors that the Large Hadron Collider could produce black holes that would destroy the Earth spread, making people nervous about what would happen once the experiment turned on. It's easy to look back and laugh now, years into data collection, the discovery of the Higgs boson, and everything else that has come out of this great experiment. But was there a valid reason for people to fear in the first place? Today on our show, we'll dive into the possibility that the Large Hadron Collider really could produce black holes or other dangerous phenomena, and also why physicists weren't that worried about it.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's kind of like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. Recently, I've been listening to a series in Wondrium entitled Understanding Russia, A Cultural History. Over 24 lectures, this course covers everything from Ivan the Terrible and Peter the Great to the role of the Russian Orthodox Church in the Revolution of 1917. It's given me some important background that really helps me understand some of the events that are going on in our world today. So if you want to learn more about Russian culture and history or just about anything else, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a month of unlimited access for free. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
It's 2008, and the Large Hadron Collider is about to turn on for the very first time. This experiment will produce the highest energy particle collisions that a controlled experiment has ever seen, all just a few hundred feet underground, Switzerland and parts of France. After spending 10 years on its construction, scientists at the time were eager to start using this machine to learn about the universe. But not everyone was so excited.
There were some really loud voices out there telling us that we should be really concerned about this machine. And not just concerned about some pollution or some local negative consequences, but of the entire extermination of our planet, the disappearance of it, the transformation of it into some sort of cosmic nothingness, and all of humanity along with that. So, this is the highest possible stakes.
So what were those opponents of the LHC trying to say? And how sure were physicists that there was nothing to worry about?
Are we 99% sure we're going to be safe? 99.9999999% sure? Even more sure? Those are the sorts of questions I want to wrestle with. Let's just start by conceding that any time somebody arranges matter or energy in a new configuration, some arrangement that's never happened before, there's a chance that something totally unexpected will happen. So maybe there's a law of physics that causes something weird to happen that we don't know about. And until we arrange matter and energy in that particular way, we don't know that law exists, and therefore we don't know this is going to happen. So we always have to be open-minded to that sort of thing. And when we operate machines like the Large Hadron Collider, we're doing this specifically with the intention of trying to study particles that are interacting with exceptionally large amounts of energy. So there's definitely a chance in these kind of exotic configurations that we might create new forms of matter and energy that we've never seen before. In fact, that's the whole point. We build particle accelerators to try to do stuff like this, try to discover new kinds of particles, new forms of matter, new forms of energy, and then to go about studying their properties. So then you have to wonder, could any of these new things we could hypothetically create in a machine like this be dangerous for the people that are working at the laboratory, or maybe dangerous to the whole Earth or for all of humanity, or even the entire universe for that matter?
So let's really dive into these ideas about what sorts of dangerous things could be created at the LHC.
In my thinking, you can break these things down into kind of two different categories. The first category is that in these collisions, you might somehow create a state of matter that's harmful.
We mentioned something like this in our last episode on extra dimensions. At the end of that episode, we learned that if some of these theories of extra dimensions are true, then we might be making lots of little black holes in the LHC.
Everything we know about these kinds of theories says that the tiny black holes that would be created would be entirely harmless, if they can exist at all. They would disappear in a tiny fraction of a second, but still, a reasonable person who hears about this might wonder how sure we are of this, and how completely confident we can be that such an experiment is a completely safe thing to do.
And it's not just black holes. There are other strange sorts of matters that physicists have theorized that could also pose a threat. For example, you could have matter made up of a large number of particles we call strange quarks. We call this kind of matter strangelets, or strange matter.
Kind of like in the Kurt Vonnegut novel, Cat's Cradle, you could create this stuff called Ice-9, and then it touched other stuff and it converted it all to Ice-9. If you created a little bit of Strangelet, there's a chance that every time it touched an atomic nucleus, it would become Strangelet 2, and pretty soon the whole Earth would be a whole lot different than it is now, and not in a good way. So these are real physics theories, okay? And you might really want to worry about them.
So that's the first category of potential risks, creating a dangerous form of matter at the LHC like strangelets or black holes. The second category of risk might be even stranger than strangelets.
The second category is that you could imagine if you created a really high energy collision, it could locally cause the universe to transition from our vacuum state into some other vacuum state.
We'll break down what this means, but it may sound familiar to you if you heard our episode about the end of the universe with Katie Mack. Vacuum state here is basically the state of the current laws of physics, the rules our universe is following, and what sorts of matter can exist in it. It turns out that the vacuum state of our universe has changed before. Not long after the Big Bang, our universe underwent phase transitions into different vacuum states. So many of the particles that exist now couldn't have always existed. If you want to learn more about these sorts of phase transitions, check out episode 49 of our podcast. So, if the vacuum state of our universe changed again, that can mean big, big trouble.
Maybe in that other one, electrons don't exist, or the photon's a little different, or any number of laws of physics could be different, and you could easily imagine that would yield this part of the universe entirely uninhabitable. So we definitely do not want to transition into another vacuum state. We definitely don't want to create the kind of harmful states of matter that would transform or destroy the Earth. These are definitely things we want to be as confident as possible we will never do in this or any other experiment.
Before you get too concerned, remember that these are far out ideas. They are worth considering as risks, but the science is very reassuring.
Nothing we know about the laws of physics so far tells us that any of this kind of stuff is possible. All right, so we don't have any evidence that strangelets or strange quark matter exists. We don't have any evidence that microscopic black holes can exist. We don't have any evidence of other vacuum states that we could transition into. But there are real physics theories out there, hypotheses, if you will, in which all this stuff could exist. So, it's a logical possibility at this stage, but we don't have any, supporting evidence for it.
Okay, but maybe you're still worried. After all, the point of the LHC is to create new physical conditions and possibly new forms of matter that we don't yet understand. What if something completely unexpected happens?
A lot of physicists have taken this sort of stuff seriously for a lot of years. There have been a lot of papers written about this stuff, and a lot of very smart people have put a lot of their personal energy into investigating like these sorts of questions. I would say that the opponents of LHC on safety grounds, I don't think give the scientific community enough credit for how much work and how much thought and how much diligence they put into this, but they really have. In terms of like official channels, the CERN laboratory, which is where the LHC is located, mandated a group of independent scientists to review these kinds of dangerous scenarios, like long before the LHC was constructed and turned on. The group issued its main report in 2003, concluding that the LHC posed no conceivable threat. And then they did a second review, again commissioned by CERN, which was issued in 2008, and basically reaffirming the 2003 conclusions with a couple of I's dotted and T's crossed. And then that report went on to another series of kind of endorsement proceedings. There was an external CERN committee made up of scientists that endorsed that report. And then the executive committee of the Division of Particles and Fields of the American Physical Society, they endorsed it. And the United Kingdom Institute of Physics and other sorts of organizations all like put their claws and teeth into this, molded all over, analyzed it carefully, and all kind of got to the same conclusion. There are not many decisions that human beings make that are this kind of ruthlessly explored and challenged before everybody signs off on them.
So what exactly did those scientists uncover that made them so confident that the LHC would not destroy the world?
Well, they had a bunch of different arguments, but I think one is particularly compelling. And that argument basically comes down to the sorts of collisions that they're going to be creating at the LHC aren't very special from a physical perspective. These are collisions between protons. They have a combined energy of about 13 tera-electron volts, which is, a lot. We want it to be as high of energy as possible to learn as much about the universe as possible. But, it turns out that energetic particles from space, like protons, things we call cosmic rays, hit the Earth's atmosphere with more energy than that all the time. When the most energetic cosmic rays that we observe hit a proton in the Earth's atmosphere, those collisions have almost 10 times as much energy as the collisions that we are trying to create at the Large Hadron Collider. So if you think the Large Hadron Collider is going to create some weird exotic thing in those collisions, then those exotic weird things should be made in the Earth's atmosphere all the time through these cosmic ray interactions, every second of every day, not just now, but, for billions of years into the past and, every moment of every day. And it's not just the Earth either. These sorts of things should be created in the moon and in the sun and pretty much everywhere else that particles are colliding at high energy in our universe. So to put it another way, nature is already operating and has been for a long time operating its own version of the Large Hadron Collider using cosmic rays.
So if we wanted to worry about dangerous things happening at the LHC, we'd also need to worry about the natural processes that have always been happening right above our heads in the atmosphere, in which case we'd just be worried all the time and for no good reason.
There are, however, a couple of important caveats to this argument. The most important of these is that if the collisions at the LHC were to somehow produce stable black holes or other dangerous objects, it's conceivable that those objects would be created without a lot of velocity, at least some of the time. So you might make a black hole that isn't moving very quickly. It'd be roughly at rest. In contrast, those analogous cosmic ray collisions would produce black holes that would be moving at almost the speed of light. Okay? It's just a matter of at the LHC, the two protons come in and hit each other head on with the same velocity, whereas those cosmic rays are one really fast thing hitting something at rest. So in the end, that black hole could be moving really fast. So you could further imagine that a slow-moving black hole might be a lot more dangerous to the Earth than a rapidly moving black hole would be.
This may sound a bit unintuitive at first. We're used to thinking about any black hole as something that'll suck in everything around it immediately. But in reality, black holes are just like any other gravitating object. And when they're small, they have very little mass. So they don't exert that much gravitational force on the things around them. It'll take some time for them to grow in order to exert more force.
So consider, for example, an extremely energetic cosmic ray striking the Earth's atmosphere and creating a very fast-moving, tiny, and stable black hole. That tiny black hole, if it was moving this fast, would basically travel through the whole Earth without very much happening, and it would just kind of escape out into space on the other side of the atmosphere.
Remember that in between all the atoms that make up the Earth is a lot of empty space. If a black hole is really, really small, it can pass through all that empty space without hitting any actual particles that make up the nuclei of all the atoms in the Earth.
A black hole that's that small would essentially fit between all of the atoms as it passed through the Earth, without really interacting at all, without growing in size, without really doing anything. So that could be harmless. That's good. On the other hand, this black hole that we might make at the LHC might be at rest. It might kind of sit around, get pulled from the force of gravity down towards the center of the Earth, and kind of just sit there and gradually accumulate matter, growing and growing and growing until it spiraled out of control. So it's at least conceivable that in this stable, tiny black hole scenario, the LHC could be a lot more dangerous than the cosmic ray interactions. That's pretty scary, right? But it turns out that we can also rule out this kind of danger, because cosmic rays don't only strike the Earth, but they strike everything else in our universe too. So let's picture an extremely energetic cosmic ray that's going to come in and strike a very dense star. Here I have in mind something like a neutron star, or maybe a white dwarf star. These kinds of objects are billions or even trillions of times more dense than the Earth, and that's dense enough to slow down even the tiniest black holes we're talking about. So the cosmic ray might come in, hit the surface of this white dwarf or the surface of this neutron star, make a little black hole, and then that black hole will plunge through the star where it will grow and grow and grow in mass, slow down, and eventually consume the entire star. We have telescopes pointed at a lot of neutron stars and a lot of white dwarfs. Furthermore, we see neutron stars that are known to be billions of years old, and white dwarfs too. So I think we can pretty conclusively determine that the cosmic rays that are striking these objects are not creating black holes of the kind that people were worried about. They're not creating strange quark matter, strange nuggets. They're not, inducing vacuum transitions. All that dangerous stuff you might worry about, if it would go on at the LHC, would also have been going on in those collisions. And just empirically speaking, just observationally, we know that's not going on. This can't pose a threat to us.
So the fact that we haven't seen any dangerous black holes appear in our atmosphere, or in telescopes when we're pointing at other stars, makes us pretty sure that the LHC shouldn't be much different. And this isn't just a hunch. The math was absolutely done here, very meticulously, to make sure the probability of making a dangerous black hole is negligible.
And basically, you only need one of these objects to conclude that it's safe, because if you find a billion-year-old astrophysical object, you know that thing's been hit by, a certain number of cosmic rays, and you know that number of cosmic ray collisions is way more than the number of collisions we'll ever do at the Large Hadron Collider. So you can be pretty, you can be rest assured. You can rest assured that that's not going to be any more dangerous to the Earth than cosmic rays are to that astrophysical object. All right, so all these, very credible and very careful arguments were laid out by, some of the world's greatest physicists. But despite, all of these, rigorous and highly credible arguments, a handful of people still tried to stop the LHC from going forward in the years leading up to its starting date. So I was a, postdoc back then. And I remember reading about these lawsuits in the newspaper, and, I'm not an attorney. I don't really know anything about law. But I did know that a lot of my colleagues were really worried about this. They were worried that these lawsuits, even if they didn't succeed, they could slow the LHC down enough, which would, not only prevent scientific progress, but also just cost a lot of money. Just a year of delay or something would be a big piece of the LHC's budget. And, we didn't have a lot of money to waste. So, there were real concerns about this. Fortunately, the legal challenges were all dismissed relatively quickly, not quickly enough, but quickly enough that the LHC could start as scheduled. And when it did, we all rejoiced and quickly forgot about our legal challenges and moved on. And then, in closing, I want to make clear that I am quite sincerely worried about a variety of existential risks that new technology can pose for humanity. I think we should think long and hard about those sorts of risks. I just don't think the Large Hadron Collider is one of them. In particular, I mean, the long-standing one is the risk of nuclear weapons in a major exchange. I think, that's something that, everybody who's lived through the second half of the 20th century and 21st century has kind of gotten used to as a standing major threat to the future of humanity. More recently, I think the more extreme versions of climate change pose those sorts of existential threats. And I think the median outcome of climate change is one where we find ourselves living in a world that's a lot harder to live and survive in, but not one that's impossible to. But there are tales of that distribution, especially if we don't take much action, which are, existential in their danger. More recently, there are, talk of dangers associated with various kinds of biotechnology or nanotechnology. I don't know a lot about those, but some smart people seem to think, we should be careful about certain aspects of that. And then there's the technology risk that I am personally most concerned about, which is some sort of runaway version of artificial intelligence, something that we can't control, something that gets it in its own mind that it wants to do something that isn't aligned with our interests. And by then, it's too smart and too capable for us to stop or control it. I would even argue that that's a likely outcome in the late 21st century. I try not to worry about it too much, but I don't succeed very well.
So, do you need to worry about physicists creating an Earth-destroying black hole at the LHC? Probably not. So feel free to focus your worries on everything else. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.